Hello, colleagues. It's my pleasure to welcome you to our leadership conference. It's my pleasure as the keynote speaker to kick us off here with an introductory presentation on electrification. We're going to really focus on what the trends are in the industry. Hope you enjoy this conference and get a chance to exchange some interesting thoughts with our colleagues here. Okay, the focus of this presentation is going to be to talk about where the next generation of power electronics and circuit protection are going to come into play here. So we'll hit on a couple of key attributes here. And I think what's very interesting about electrification is we're really following the electron, where it's generated within the power plants and then how it flows through the system, feeding into businesses, feeding into different types of industries, but ultimately the focus of this conference is getting it into a vehicle and then potentially back. And that's what Eaton's core strength is. You might be interested to know that over $13 billion of our $21 billion in sales is supplying electrification and electronic solutions into the industrial market. And we're blending that with our electrification know-how in the vehicle to really bring together system solutions. What we'll talk about here is focusing on where we're trying to see the market head. What are some of those key technology areas? And then focus real specifically on a category called power electronics and circuit protection, and looking at how do we achieve power density improvements, which is how we're going to achieve efficiency and miniaturization of these types of components, which ultimately will also lead to better cost. Some of the latest market trends are showing a real significant growth in electrification. This is the latest study that's been published from IHS. And despite a very difficult year in 2020 with COVID impacts, it might be very interesting to see here that electrification is growing very, very strongly. And that's suggesting that the consumers are adopting, but also that the automakers are focused on the transitionary technologies like electrification. You see here from the slides that 48 volt has grown very significantly, almost 12-fold, 13-fold, while pure battery electric vehicles, the market has significantly increased 7 to 8 times its magnitude. And the year-over-year projections continue to grow each year as we revisit these types of forecasts. Ultimately, we see battery electric vehicles and 48 volt vehicles, mild hybrids, taking on the sizable part of the electrification market. And of course, that's to do a couple things, to achieve lower greenhouse gas emissions, as well as meeting very stringent tailpipe emission standards. So what are these trends? What are we really trying to focus on as an industry? Historically, electrified vehicles were thought of as compliance vehicles. And as compliance vehicles, the automakers didn't have to focus so hard on cost, but they were trying to get the vehicles out into the market to get the experience to achieve and leverage credits that were available in the market. But as they become more mainstream, of course, cost is king. And we have to also deliver no compromise to the end customer. So what does this mean? This means that these types of technology trends are really required to drive the market acceptance. The first one, without a doubt, is safety systems. And that's a real critical factor as we're looking at trying to win over the consumers. Will they accept it? How do they look at a new technology? Safety is king. And coming from a company with a circuit protection background, it's really interesting to look into those types of insights and consumer tendencies. But ultimately, as we start moving the paradigm and it becomes more acceptable, cost becomes the ultimate issue, the no compromise performance, as we mentioned. But how do we achieve these things? And that's where efficiency comes into play. And efficiency is certainly a function of power density. When we look at the types of technologies that we'll focus in on today, we're talking about really 3 different types of classes of components here and subsystems. The first one being the inverter. Now, the responsibility in the inverter is to convert the energy that's coming from the battery, which is DC, into AC to drive a motor. Or in other cases, to actually export that power. That's what we would call an auxiliary inverter. The other types of power electronics in our vehicles are chargers and converters. Chargers are, of course, required to charge the battery that's inside the vehicle for plugins, and converters are necessary to support multiple board nets. We might have a 400-volt battery or 48-volt battery, but we still have to power the other consumers in the vehicles, which are running off of 12-volt. So that's what those converters are doing. And then on the circuit protection side, we're very focused on how do we anticipate events, and how do we handle unanticipated events that may cause safety concerns. And that's, of course, where fuses come into play, and new technologies like BreakTor, which bring together kind of the best of both worlds for contactors and pyros into a single package solution. And putting those into junction boxes where all these interfaces, high voltage, actually occur. So with that kind of frame of mind set, what are we talking about? How do we achieve efficiency, and how does that ultimately lead to power density improvements? And I wanted to really talk about 4 high-level categories here. The first one is reducing the switching frequency. Now, we hear a lot about in the market, we hear things like silicon carbide, gallium nitride. And the reason why these technologies are interesting is they're addressing switching losses, which is what is really going on in the background of these systems doing these electrical conversions. That's what we mean when we're talking about switching. The other part of semiconductors is as we pass current through them, they generate lots of heat. So that will be the other focus area for us as an industry, is how do we get the heat out of that system as fast as possible and also very cost effectively. And once we establish those types of, let's say, baseline systems, at the component level, we're seeing very interesting technology wave happening now, where the components are more capable, but they're also doing multi-functions. So now we can talk about how do we get to integration at a component level to unlock more functions and features in a smaller package. But ultimately, where we clearly see a major trend is what we would call system functional integration. This is where we're taking different subsystems and putting them together in the most optimized package. It's almost like putting pieces of a puzzle together to make a perfect picture. That's really what we would call subsystem functional integration. And we'll dive into these trends here so you can get a feel for where the technology is headed. So when we talk about switching losses, we often hear about things like the Tesla Model 3 adopting a silicon carbide inverter. And silicon carbide is one of those buzzwords in the industries. And it's very, very important because it's creating this trend towards achieving higher efficiency by reducing the switching losses. If you follow the graph on the right, that's showing what a silicon carbide power module inside of a traction inverter. So this is what's powering your motor. And it's showing what the differences are at different loads, essentially how much power and torque you're requesting, and what the benefits are over a traditional silicon IGBT power module. And you can see there, the blue is really indicating the differences in the switching. And then the orange here is representing the difference in the conductive losses. And you see that as the load increases, there is an improvement in the switching loss reduction as you move towards silicon carbide. Now, as you get towards gallium nitride, which is a more advanced material, we see very similar types of directional trends, essentially more benefit. So what does this allow us to do? When you're looking at the silicon IGBTs today, and again, they're used on inverters, they're used on chargers and converters, they're sizable. They have a certain surface area and volume that's sitting inside these devices. And again, they can only let so much power through them before they're limited at a certain temperature. We call that the junction temperature. Now, if you move towards silicon carbide or gallium nitride, you're now able to get more power through the device And that allows us to essentially shrink it. And again, that's because we're able to reduce those losses. And that's what you're seeing on the bottom right corner there. You're seeing the to scale what the size difference would be going from a silicon to silicon carbide. Now, the issue here is that there's certainly some cost impacts at a component level, but at a system level, a silicon carbide inverter actually results in more efficiency, and also more efficiency in onboard chargers and DC-DC converters. So at a system level, the cost parity is going to come sooner than later, especially as our colleagues in the semiconductor industry reach scale, production scale on silicon carbide wafers. The production price parity will come quite soon is what we suspect, and we'll see more products adopting this. Now today in the state of the art, by I would say 2022 to 2024, it's very likely that your high voltage onboard chargers and DC-DC converters will have silicon carbide, potentially moving by 2030 into adopting gallium nitride. So these things are happening at quite a rapid pace. Now, what's the other step here? So we know the cost of these types of components are very high. So we have to make sure that we're using them most optimally. And that's where the second focus, besides reducing the switching losses, has to be on optimizing the heat rejection. That's the name of the game here, is how can we get heat out of this system as fast as possible? And we really have a couple of weapons in our arsenal to do that. The first thing is we got to maximize the surface area of our cooling systems to try to pull heat away from these semiconductors. And now we're going to look at some of the ways to do that. How do we optimize what we would call cooling plates? And then what are some of the tweaks we can do to achieve improvements in performance, 1%, 2%, 5% potentially, to bring the heat out of the system? One of the popular trends in the industry, coming from a material perspective, is something we call thermal interface materials. Now, these are, as you can see from the slide here, these are materials that would sit on the silicon or silicon carbide power modules, and their job is to thermally conduct heat away from those systems to a cooling system. In this case, of course, in automotive systems, we have coolant that's running throughout the vehicle at relatively lower temperatures to essentially pull heat away from this type of system. Now, the graph on the right is going to show what it means to actually have TIM material, thermal interface material, and looking at key properties called thermal conductivity. You can see as we increase the thermal conductivity, as you would expect, we're able to pull heat out of that system. And that's critical. That means that semiconductor can run basically more current through it and not hit limits at their junctions. And so that's what we're trying to achieve here. Another approach, material, again, is now investigating what is the right type of cooling plate material within the system, or anything that's basically interfacing in between. In many of these cases, the cooling plates are made from different types, different grades of metals, typically aluminum. Perhaps you can blend in some other materials depending on those thermal conductivities. So again, this is where you would take a look and say, okay, how do I achieve the most cost-effective material solution to pull away heat? So again, you're seeing a lot of the know-how that's been in the automotive industry for decades, but now laser focused on electrification. And that's why this industry is so exciting right now. So many different solutions in the market. Eventually, what you'll see is perhaps even eliminating some of these materials. So the next generation, for example, we may actually eliminate the thermal interface material and go straight from the silicon directly to copper, for example, a directly bonded copper, to reject that type of heat. That's how fast this industry is evolving. Now, when you look at the cooling plates, you're saying, okay, what is that? Essentially, what we're trying to do is take that silicon or silicon carbide and sandwich it with this metal high thermally conductive material that also allows coolant to flow through it. And that's what you're seeing on the top right graph there. You're seeing that sandwich of the semiconductor, this plate system. And they're complex, of course. And that's the idea here, is how do we optimize these types of designs? Now, what you would see at the very tops, at the surfaces of these plates, is you would see something we would call pin fins. And it's very much like a fin on a shark. We're trying to optimize the surface area of these cooling plates such that we can reject heat. Now, if you think of these almost like windmills in a field, you're setting up these windmills such that when air passes through, you're creating this interesting turbulence to maximize how much heat you can remove away from the surface. That's what the bottom right figure is showing there. It's showing you can create different types of fin patterns, something you would consider to be quite simple, but this is really heavy computational fluid dynamics at play here that are able to look at how do we bring heat out of the system. Again, something the automotive industry is just excellent at, but now applying it to the area of electrification. Now, once these are all together, now we have a little bit more freedom at a component level. We're no longer maybe heat limited, so we can run these things a bit harder. And now that brings up some opportunities for integration of components. And then eventually integration at a subsystem. One of the key examples that we're seeing in the industry adopt today, so you'll see these in production, is the adoption now of integrating onboard chargers and DC-DC converters. And that's what we're showing here on the bottom left. On the very top, a DC-DC converter, a standalone, and then on the bottom, a standalone onboard charger. On the right, we now have a fully electrically and mechanically integrated system solution. And the way we do that is we're using something called integrated magnetics. These are magnetics that are performing both the functions of a DC-DC converter as well as an onboard charger, but in one magnetic. That's where the trend absolutely is. But what else are we able to achieve? As you can see, it's one mechanical enclosure. It's fewer connectors in terms of how do you get power in and out of that system. It's using one cooling plate and even one electronic controller board to control both of those systems, as well as communicate outside of a vehicle. So what did we achieve here? We achieved power density essentially by eliminating one whole component here, but we've also brought down the cost of the system by eliminating essentially redundant parts and redundant components that we no longer need because we have multi-function. So how do we do that though? And where will we head as an industry? What you'll see in the figures on the left is where the magnetic technology was, and let's say is today, and where we will head in the very near future is now bringing together this manufacturing prowess as well as electrical system and mechanical enclosure design. We're able to bring together essentially three different functions within these magnetics and bring them all into one package. Now, it looks pretty simple. It's a very complex design, but it's very easy, let's say, for the tier ones, the suppliers, to now take this type of technology and integrate it in the system. It's fewer components, which typically means the reliability is better. But also here, in terms of heat rejection, we can now focus a special cooling plate design instead of trying to address three different pieces of the magnetics, now focusing on a single magnetic. The other part that we're seeing in the industry now is trying to really look at where the trend is in terms of power and then designing the components to achieve specific power levels rather than scalability. So when we first looked at onboard chargers in the market, we had different types of power levels ranging from 3 kilowatts all the way up to 11 kilowatts. Now we're actually introducing all the way up to 22 kilowatts. And one of the ways to address this was to achieve 11 kilowatts, but the scalability to 3 is we would stack what we would call magnetic bricks in a 3x3 fashion. As a matter of fact, 3x3.7 to get to the magical number of 11. Now we're saying, okay, let's start moving the trend towards the 11 kilowatt as we can start getting these things more cost effective, but also because the industry is moving from plug-in hybrid vehicles to battery electric vehicles, we need more power in that charging system to reduce the charging times. So now the market has created more higher power solutions. Now we can find 5.5 kilowatt magnetic components in the market, and also what we would call a single 11 kilowatt magnetic in the market. And now you're seeing higher power available in the market, but not only to do one functions, but actually to do multiple functions here. And when you're comparing, let's say, the same power levels, you can see that we can create something somewhere around a 13% volume savings just in the magnetics. Now at the system level, as we discussed, your savings are much, much greater as you're eliminating connectors, controller boards, which are printed circuit boards, as well as cooling plates. So quite a lot of optimization that's occurring here. And the integration is only becoming more rapid, and the degrees of complexity are increasing, I'd say, almost exponentially. And that's a lot of fun, because what you're seeing is automakers and suppliers coming up with really advanced functional architectures. That's how do we put these building blocks together to make that final puzzle picture. And the fun part of the market is each automaker in tier one has kind of their own views on how to get there. And that means more and more solutions coming into the market. This is a great picture that illustrates where this complexity is headed. Whereas previously, when we talked about electrification system integration, we called it a 3-in-1. And that typically meant a motor, an inverter, and a gearbox. And now when you say 3-in-1, the first question is, well, which 3-in-1 are you talking about? Are you talking about that motor, inverter, gearbox, or is it something else? And guess what? There's 4-in-1s, there's 5-in-1s, there's 6-in-1s. And the opportunity now is to bring in some of those circuit protection elements, instead of scattering them in a vehicle, actually now bringing them into the mix, making them closer to where the critical high voltage components are within the system to bring down the cost. So you no longer have to run high voltage wires way across the different types of systems. So what's being illustrated here is an exploded view. And this is showing an onboard charger, a DC-DC converter, as well as a power distribution junction box, all sitting in here with a resettable contactor that we would call a breaktor. And this is a system that allows you to quench energy and really protect the system in safety critical applications. That's the technology that breaktor is able to bring to the table. So in fact, breaktor is actually eliminating two components within itself into a single block. But the future is not, again, these separate types of components, but now it's bringing it all together in a very simplified, high power dense type of package. And that's what you're seeing here. This is a very significant savings, around 20% power density improvement. The lowest possible cost, because we're eliminating the run of parts. We have a single controller board controlling all this different types of functionality. We're cooling it using a single type of a system. But maybe more importantly, the safety is built all into this system. And so if there's anything that goes wrong, it's innately built into the system to be functionally safe. And you can see how we're now achieving those trends, bringing safety first, achieving the power density, bringing efficiency to the table, and all while bringing the cost lower, and even maybe as importantly, making the assembly of these vehicles simpler, which obviously drives the cost down and also improves things like the reliability. So where does that leave us? Very exciting time for sure. The first thing is, we know that the industry is moving towards more power dense solutions. And the fact is the technology is keeping up. The technology exists for us to do that. And it's really led first by wide bandgap materials. Moving towards silicon carbide and gallium nitride will happen. Cost parity in those will happen. The question is when? Is it now? Is it 2025? Is it 2030? And what power levels? What voltage levels? Those are the areas where it's very exciting because there's so much development and competition going on. The second focus area is heat rejection. How do we optimize our system, use all the know-how we've built in the automotive industry for 100 years to now focus on electronic heat rejection for these high power systems? Lots to go on absolutely in that area, including advanced materials. But perhaps the most interesting is looking at how the component integration will occur. And we just touched on a couple of those topics today. There's more and more types of technology on that horizon with that same type of philosophy. How do I bring more functions and features within the same types of functional blocks? But ultimately, I think what will differentiate the automakers and what will differentiate the tier 1 and tier 2 suppliers is who has the more interesting functional architectures, who will bring together these 3-in-1 to 6-in-1 and who knows, X-in-1 types of solutions, who will usher in the most cost-effective and high performance, high quality types of solutions in the market. It's an exciting time, and I think that's what we're here to really explore. So really appreciate your time here, and looking forward to virtually meeting and talking to this full community together. Thank you for your time.